the number of people is not so great because they are, as I told you, very selected ones. And, I'd like also my students from Terra to come. They have come, and tomorrow probably we're going to have 2 more people that today are involved in another kind of lesson or something like that. So, please.
Thank you.
That's your time.
It's a pleasure to be here. It is not the quantity that matters, the quality. But if we have a dozen future leaders in the world, and I can clone.
I think that I have got a logistic suggestion. Please move in the very center.
Be able to see it in
Just to be able to better see the main goal. We're going to also to reduce the heat because
it is a little bit hot, I know that.
Since Professor Akbari gave us the allowance to record this presentation, we're going to put it on our internet site, and we suggesting to speak in the microphone in order to better record his talk.
Sure.
If I find it.
You find it. Without microphone?
Yeah, no, we can start.
Okay, that's good. A couple of basic rules. Let us make this thing two-way communication rather than just one way. If you have questions about clarity of some of the things that are showing, you can interrupt me and ask me questions right away. And if we have discussion questions, I would decide how long the discussion would go on with the interest trying to cover the material as much as I have. All this presentation that I have is available to you. You do not have to copy it. Copy is being going to be saved in here. I will be more than happy to send you a PDF file of it by just dropping an email to Hashem.Akbari@Concordia.com. So the particular presentation that I have designed for today is for about 1.5 hours, including questions and comments. And the idea is to try to give you a complete round view of one aspect of the research that can have different notations in different environments. So as an example, as the title shows you, cooling urban areas, then talks about an integrated research and implementation. There are completely two different fields that we are trying to bridge it in this research. We are focusing not only on energy, we are also focusing on air quality, and also we are talking about technologies that can reverse or counter some global warming. So, material development is also an integral part of this research that I have chosen not to show it in here, because the title would be even longer than what I have. So, I would be introducing the topic to you and try to present a picture, Madonna's box here and there, and then I would cover one or two topics in each of those areas that for you to get a general flavor. On tomorrow, I will be talking for 2 hours, only looking at one aspect of the research, which is material development for pavements and roofs. So it is an integrated program. For those of you who may not be familiar with the terminology of heat island, it is a name given to the cities because cities are warmer than suburban areas. You all know that even in the old days, during the Roman Emperor time, they were having summer houses, summer vacation houses, because they knew that in the rural area it is more comfortable and cooler. So the moral of the story here is that it is not something that we have discovered right now. It is something that we have been able to quantify it more and more accurately recently. So here are some measured data that showing that cities are indeed warming up. And what I have in here is looking at the change in the temperature at the center of the cities and looking at that growth in the change of the temperature for every decade. As an example, if you look at Los Angeles, California, it has been growing at the rate of about 0.8 degrees Fahrenheit, this is the scale Fahrenheit, or about half a degree Celsius every 10 years. So that would mean within the last century, the downtown Los Angeles is about 5 degrees Celsius warmer than what it used to be before. Obviously, that trend is not going to increase forever, but the size of the city is expanding. There were times that Los Angeles area had a population of only about 500,000 people. That is about 70 years ago. Now Los Angeles area has something like about 15 million people. And they are all going to be influenced by the so-called heat island effect. So these data are being shown for quite a few cities in the United States, and I also added 2 cities in Asia, China, Shanghai, China, and Tokyo, Japan. I'm quite sure that there are such data also available. So Roma, Milano, and Florence to study if it's not already been published. So why are we interested in the so-called heat island? As the temperature increases, the demand for cover, particularly if it is summertime cooling, also increases. This is the hourly data at 4 p.m. in megawatts shown. The data is almost 30 to 25 years old. That up to about temperature of about 20, 21 degrees Celsius, the base load in Southern California was about 10 gigawatt of power. But as this base load of 21 degrees Celsius goes to 30 degrees Celsius, for a period of 9 degrees Celsius temperature difference, the power demand goes as much as 15 gigawatt. So this difference of 5 gigawatt is nothing but air conditioning. And if we say that 2 or 3 degrees of this temperature is because of the urban heat island, so that would mean we can easily drop this thing, if there was no heat island there, by about half a gigawatt during the summer break. We are going to discuss these numbers, putting them in context as we go forward. In greater Tokyo area, for every degree rise in temperature, there is an additional 5 gigawatt of power needed. So if they have a heat island of 2 degrees Celsius, that's 10 gigawatt of power. This is power required to do something that we have done wrongly. If we were careful from the beginning and we have not created the heat islands, we didn't need this power. The cost of each gigawatt of power is minimum $2 billion. So in a period of 100 years, we are spending, say, $20 billion additional power because we have not designed the since properly. And of course, all these power plants are using fuels, and their fuels produces emissions. The emissions are greenhouse gases. Greenhouse gases would make the global warming, and we have not only the heat island effect, the global warming effect, those effects together. So, energy and electricity.
Here is the microphone.
Perfect.
You have only to apply to an engineer, not to an. Thank you.
No, that's quite all right. Now the problem is that I need to lower the, oh, you're doing that? Good.
I'm trying. I don't need to do so much. It's fine now?
Yeah, it looks fine to me. There is no,
Okay.
good.
Last
No. So, one aspect of urbanization is also characterized by what we call it as a smog. The urbanization comes in production of combustion machines, such as cars, and then you also have volatile organic compounds. These emissions react together and they create a very dangerous gas which is called ozone, or in short, smog. Smog has huge negative consequences, but it is mostly, not mostly, it is clearly a man-made effect. So now, again, if you look at the scale of the ozone formation versus temperature, this is ozone formation, this is temperature, it looks like you are cooking something in your kitchen. You have the ingredients which are NOxes and volatile organic compounds. These ingredients cook faster in higher temperature. At lower temperature, they cook a lot slower, so they produce less smog for you. So at the temperature of about 25 degrees Celsius, the number of smoggy days in one part of Los Angeles had been very, very small. But by the time that the temperature gets about 35 degrees Celsius, practically always a snuggie. So again, if you have managed to cool down the cities by few degrees, you would be able to reduce the fraction of the smoggy days by something like 30%. Now, how important that is, very important, and that's the reason that we are getting to the aspect of the air quality. In Los Angeles basin, if you cool down the city by about 3 degrees Celsius, the effect of it is the same as making all the cars electric. You know, just think about it. One choice is to cool down the cities by simple measures of cool roofs, vegetation, cool pavements. The other is spending $2,000 per vehicle to make them electric. Which one is more attractive? So, a lot of air quality management districts are making heat island countermeasures as mandatory and basic principles for their energy and air quality program. So at this stage, we were ready to start looking at this program as a comprehensive way. So suppose that in my house, I have a cool roof. That during the summer would reduce the temperature of my roof, conduct less heat into the building, and therefore I have lower demand for air conditioning. Lower demand for air conditioning would require less power from the power plants. Less power from the power plant would require less energy in the boilers, less emissions from the power plants, and lower NOxes. Now, if you have many of the buildings within the city or community apply cool roofs, also you would make cooler pavements, and you also produce a lot of shade trees within the city, all the traditional things that we have been doing for thousands of years, that would reduce the temperature of the urban area by a few degrees. Now, if your house happens to be in a cooler environment, it would require less energy, you would follow the same path. Now, if you have less air temperature, that would slow down the formation of the smog, that improves the air quality. And very recently, within about 5 to 6 years ago, we have also found out that cool roofs and cooler pavements, by directly reflecting the short-wave radiation back to the space, they counter the global warming. So these are some of the specs that I'm going to open below for a few seconds, let you an insight to it, and close the door going to the next one. So what is the city made of? A typical new city in a developed country is made about 25% roof area, about 35% of the paved surface area, and all the other surface area are less than 40%. So the man-made surfaces in a typical surface area is something like 60%. I dare to say that in cities like Perugia, the portion of the roofs and pavements, because they are more concentrated, are even higher. As an example, if you look at the older part of the Perugia, you see 100% paved surfaces and roofs. There is practically no vegetation except in the surroundings. So, to a certain extent, this depends on how you define the different cities. But the story to take from this study that we have done, and this study has used high-resolution orthophotography at the scale of 10 centimeter to 30 centimeter, and getting samples from the many urban areas and identifying those samples in 22 categories and summarizing those samples into the 4 categories. the higher the reflectivity of a surface, the cooler that surface is under the sun. We all know that as the first principle of the physics. Or the other way around, the higher the absorptivity of the surface, the hotter it gets under the sun. A dark black, dark asphalt absorbs 95% of the incoming solar radiation, and if it is applied on a roof, it can be as much as 50 degrees Celsius above the air temperature. A white roof, on the contrary, at the maximum would be about 10 degrees Celsius above the air temperature. Also note that metallic roofs, even though they have much higher reflectivity, but because of the low thermal emittance, they can get also very hot under the sun. You have all touched a piece of metal, shiny metal in the sun, and you have all burned your hands. So this is a burnable memory from all of us. So when we started this research, the first proposal that we wrote, the comment to that came in, oh, everybody knows it is cooler under the tree. What is the research element? And now, this is interesting, 30 years to be exact from then on, we have about 3 dozen institutions throughout the world that are doing this research that some policymakers 30 years ago were saying that it is no value. So in order to start making these things in a systematic way forward, we started first looking at the roof surfaces. So we took several examples of a typical roof. This is a type of roof which is called cap sheet. The cap sheet is an asphalt fiberglass road sprayed with a very small size of about 2 to 3 millimeter granules. So the reflectivity of a cap sheet like this with typical granules is about 20%. So we cover this surface with a coating with a high reflectivity. And this is showing a thermograph of that section of the asphalt roof, say a section from here. Note that on the overlapping areas, you see nothing but the asphalt. And so we are covering this part of the area with a white coating. And of course, we do that for the entire roof, but taking the picture of an area that it is coated and not coated, and that is being shown in here. The area that it is coated has a low temperature of about 38 degrees Celsius. The area that it is not coated has a temperature of almost 85 degrees Celsius. The areas that are on the asphalt range, they are even much higher temperature. So this proves that indeed the cool roofs work. So we conducted many experiments. We are going to talk about this thing later on in tomorrow's lecture, that we carried out several experiments side by side and documented energy savings. Then it came to the question that who would like to apply a white roof on their building? So we had to answer that to the practitioners, to the communities. We said that, look, this is a picture in Bermuda Island, and all the roofs are covered with white chalk. This is basically gypsum type of coatings that they apply, and they use the water from the roof and they collect it for drinking purposes as a potable water. And the side benefit that they get is they will be cooler. Of course, every now and then they will find out that a roof is getting a little bit moldy and darker every 10 years or 15 years. They put a new fresh layer of coating there in order to keep it as nice and bright as this one. None of these buildings have air conditioning, very comfortable. Then we showed people that even though you do not like to have light colored roof on your own building, but you are willing to spend $10,000 to travel to a Mediterranean island to see white cities. And indeed, they are looking very, very attractive. This is a picture that I took myself in Santorini Island. And the building, not only the roofs, but also the walls, they are all in white. None of these buildings have air conditioning. The only buildings that typically have air conditioning in Santorini are hotels that are for the tourists that they come there and they have very low tolerance. In developing countries where the price of energy is the same as anywhere else in the world, but the price of labor is much, much lower than the price of energy comparatively. This kind of technology is making a lot of sense for them as the economies, as an example in India, is expanding. Some people can afford air conditioning. So the very first question that the smart one is asking is that, is it cheaper to install a white roof or buy an air conditioner? Because both of them give me the comfort that I want to have. And they are finding indeed it is much, much cheaper to install a white roof and maintain it, and rather than buying air conditioning and paying 15 cents a kilowatt hour in order to cool our building. We did an experiment in Hyderabad, India, that we covered two identical buildings, one with a dark color roofing material, one is with the white, and then look at their energy performance side by side. For those of you who are interested in monitoring, particularly for field monitoring, you would notice that in field monitoring things are very, very difficult because there are many, many variables that you cannot control. And if you try to really put instruments to document the effect of all of those variables, it will be very, very expensive proposition. So physicists have this experiment which is called flip-flop experiment, saying that you look at the performance of two objects under the similar condition, and then you do something to one of those objects to see how the performance changes. Then you do the same thing on the same object, and then the performance should be equal. And indeed, we had a flip-flop experiment that we monitored the energy performance of these two buildings before. Then we installed a white roof on one of them, and suddenly find out that the performance changed significantly. As an example, in the area that building east was using 400, building west was using 450 kilowatt hours or 480 kilowatt hours. By installing a cool roof on the west building, that level of consumption came back to 400. So we documented a savings of 10 to 20%, and since then we have been able, with the help of many colleagues throughout the world, to make cool roofs as part of the reality of the life, which I'm going to discuss of the reality of life in many countries all around the world. So when I come to this question, a lot of people immediately ask me, what about heating? How many of you have that question in your mind at this time? None of you? Okay. In cold climates, people believe that if cool roofs work well in the hot climates. In cold climates, hot roof would work better. And that's myth that people believe, but they do not look at the science of it. And here is some of the basic rules that we are finding out. Obviously, when you install a cool roof in any place in the world that requires air conditioning during the summer, during the winter, there is a chance that your heating energy will consume. But the further north you go, that less that chance becomes, and I'm going to explain it why that's the case. So the rule of thumb is that a cool roof, anywhere that you need air conditioning in the world, during the summer, you need heating during the winter. Cool roof would save you money. There is some part of the world that you may have to spend out of that 100% of your savings, 30% of it on your additional cooling during the winter, but still on the net you would save 70%. If you do not have a cool roof during the summer and the comfort is not an issue, obviously a cool roof would not save you energy. There is no question on that. If you are considering to buy an air conditioner, first consider a cool roof. And another big factor is in here. A cool roof would help you to downsize the air conditioning for your building. A downsized air conditioner in your building, particularly the air handling units, during the winter time would operate more efficiently. Therefore, there is a potential that we also save electricity saving during the winter. Also, we are going to discuss that cool roofs would cool the globe. Why the winter penalties are not that important, here are some of the reasons. Everybody knows that in those cold climates, days are half shorter than the summer. In Montreal, during the summer, you have 16 hours of sunlight. During the winter, you have 7 hours of potential sunlight. The sun angle on the roof, the further north or the further south of the equator you go, is lower. The sky is typically 3 to 4 times cloudier. Most heatings in cold climate happens during the night, when the roof color doesn't matter. So, on top of that, at least for 50% of the cooling season, your roofs are covered with snow. So when you account for all of this effect, you will find out that the winter penalties during very, very northern part of the globe is really, really small. In examples such as Toronto, the Ontario Hydro is a winter peaking utility. Now, they have changed from winter peaking utility to summer peaking utility because a lot of new construction come with air conditioning in the building. These air conditioners only operate for 1 month of the year, and the utilities have to spend significant amount of money to provide additional capacity for that 1 month of the year. A cool roof would make the building comfortable for at least half of those buildings and at no incremental cost. So at this time, we are now about 5 years ahead in our research. Then we are satisfying many communities that cool roofs, white roofs, lend themselves easily to commercial flat buildings that nobody is seeing the rooftop, and why not using it? Then we show them some pictures of very, very high class buildings that are white and very attractive. Then still people, because of architectural aesthetic, would like to have color on the roof. At that time, we came in with the ideas of making cool color roofing materials. This is actually an example of a cool color roofing material that we installed back in early 90s and tested the performance. So what is a cool color material? If you look at the spectrum of the sun, you would find out this is a spectrum for the Northern Americas, but also applies very easily to the condition in Italy. About 5% of the sun's energy that reaches the earth is in ultraviolet. About 43% is visible. We define color by the performance of these surfaces with respect to this 43%. And over 50% of the sun's energy reaches the Earth's surface in the form of near-infrared that's not visible to the eye. So it doesn't affect the color, we do not recognize it, hence the definition of the cool colors. So we put a goal for ourselves, let us try, at least in the lab, to develop a jet black surface that has a reflectivity, only an interface reflectivity of about 4 to 5% in the visible. You all know that because of the change of the density of the air and the surfaces, you have some interface reflectivity that it is calculated to be about 4% for most diffuse and direct radiation. So, yes, therefore, the jet black surface absorbs all the visible energy, but we would make this surface 100% reflective in the near infrared. Now, by definition, we have defined a jet black surface that has 50% reflectivity. Most current colored materials, they are not even approaching 20 or 30% reflectivity. Now we are designing a jet black surface with 50% reflectivity. And indeed, this is an example of it. Two browns designed to have exactly the same colors. And when you look at the spectral properties of them, in the visible, as it is expected, they are identical. But in the near infrared, the one that it is designed to be cool reaches gradually to about 80% reflectivity. The standard one is around 10%. So on the net, the solar reflectance of this surface is about 8%. This one is 27%. If you put these under the sun during the hot summer day, this surface is going to be 10 degrees Celsius cooler than the other. And here is the beauty of these things. Some manufacturers were using these materials, we didn't even know that they were using these materials. So when it comes to the black, that it is being used in many applications, particularly in Southeast Asia, that they have black roofing tiles. We tested the performance of a particular coloring agent, which is called dioxazine purple, in very, very diluted amount of, it is purple, but once the concentration passes about 3%, it is black. We applied it on 4 different backgrounds. Now, one of them was on a metallic aluminum background with a reflectivity of almost 70%. One of them on a very thick white background. One of them on a thin white background. And finally, one of them on a black background. As you see, the color of all of them are black. They are designed to be that way. And when you look actually their spectral performance in the visible, they are identical. But as soon as they become approaching the near infrared range, note that the one that is on an aluminum background stays at high reflectivity as much as 95%. On a white background, peaks up to about 90%, but gradually drops down. On a thin white background, they peak up to about 70%, and they come down. So if you look at the reflectivity of this and this, is around 40% black reflectivity versus a standard reflectivity of 5%. So with few simple experiments, we were able to reach our 80% of our goal. Remember that when I was setting up this, defining this thing, say that let us design a jet black surface with a 50% reflectivity. Now we are having in here a black surface with 42% reflectivity. So this is a time that most of our group pat themselves on the back saying, good job. So let us go and get more money to do more job. So then, good. Is this a research that only being done in the lab? That has not been our motivation in my group when I established the group. I basically was saying to myself, mostly my staff, that our success is not going to come by the number of papers that we write. Our success should be calculated by how many kilowatt hours, how many gigajoules we save. So if we do that, then we can consider ourselves good environmentalists, good scientists. So we have never been interested in doing science in the abstract. We have been trying to reach and bridge the gap between the industry and the science and bringing products to the market immediately. So initially, the material developers were dubious of our intention. They were very secretive, but as soon as they find out that we are the best friend that they can ever have, we are not asking them for money, we are just asking them to use this technology to expand their market, we were getting a lot more proposal of marriage that we could ever afford it. Okay, so we sometimes becoming to be working at the one single time with 30 different manufacturers of producing the same market product, and they all trusted us enough to making that we are not going to cross-share their product and their secret with their partners. So there were times that we had something like 30 husbands. So these are examples of cool roofing materials that are applied for the tiles versus a standard one. This particular material lends itself very well to communities in Italy that they would like to every now and then rejuvenate their roofing materials. They wash it to make sure that the mosses are going away, and they also sometimes coat it. So they can use some of these coatings in order to rejuvenate the roofs. Tiles that are being made, now there are a lot of cool tiles that are coming in, and they have all of them on this assortment of colors, reflectivity of over 40%. Metallic roofings are one of the easiest ones ever, particularly if they are being factory coated. They are already using the coatings. All you got to do is just to make sure that there is nice reflective undercoating, and then on top of that they use a cool coating. Back in 2004, 30 manufacturers in California has completely migrated from a standard roofing product to cool colored metal roofing. Because the cost was the same, there were more market for this. These materials were lasting longer because they were operating at the cooler temperature, and the customer could not recognize the difference between them. Then why in the world spend money in having two warehouses You have one warehouse, everything there. And back in 2004, we also, the first manufacturer, L Corporation, that later on was bought by GAF, started producing cool-colored shingles. These cool-colored materials became so popular that other end users start using them. These are cars, 2 cars in 2000, others of 2005 or 6. They were shown in Tokyo, and one of them was about 10 degrees cooler than the other. Some of you who may be driving or riding a motorcycle, you know that during the highest speed you need a leather jacket in order to protect yourself from the wind. But the very first thing that you do as soon as you get off the bike, you open the zipper because it's so hot out there. Now, BMW is manufacturing cool jackets. A little bit expensive, but there's no reason to be expensive because they are only making it unique, and you can also have the arm of the BMW on there. It would make it more interesting. More recent technologies that, again, at the market that is coming in, it is materials that look dark from the street but reflected to the sun. This is called directional reflective roofing materials, and these are some examples of it. These two are exactly the same. One of them is taking the picture from this angle, the other is taken from 180 degrees angle. So the sun sees this, the street sees this, the sun sees this, the street sees this. So therefore, your roof is the color that you want because it looks like that from the street, but it is a lot more reflective. And the trick behind this kind of technology is have color pigments only on the directions that it is seen from the street, but not on the directions that it's not seen from the street. In addition to that, there are other products that are coming, not to the market, they're experimental as well, thermographic. These are thermochromic, pardon me. Thermochromic materials are materials that change color with temperature. And most of these materials are organic based, and they lose their potential within a week to no more than 2 months once they're under the sun. So making it inexpensive so that the people will be able to use it on the roof is a big challenge. Another material that my colleagues in Perugia and other colleagues in Japan are also working is retroreflective material. These retroreflective material like the reflectors on your cars, which reflect on the direction that the light comes in, so they would reflect most of the radiation back in the direction of the sun, and from the street level they have the darker color that they shoot. Another technology that it is being used is corrugated metals. By the way, these are already available in the market. These have come into the market within the last 2 or 3 years. And we are proud to be part of this evolution. So in this one, the vertical part of this corrugation that it is being put as an angle on the roof are seen from the street. The horizontal part are seen by the sun. So they are a lot more reflective in the direction of the sun. So now, at this time, we have said, okay, we are about solving 25% of the urban surfaces. What about pavements? And pavements is a lot more difficult things to do because of several reasons. Number one, asphalt is not a byproduct of the refining product. refinery, asphalt is residual of refining. It is something that they have to get rid of. And of course, it does have some good quality, as many residuals have it. They have found a way to make it stabilized and mix it with granules and make all our pavements. Therefore, the pavements that have been installed throughout the 20th century, they are all asphalt pavement. And no wonder they are so inexpensive. If you want to ever find petroleum companies, do not let any pavements to be installed, asphalt pavements to be installed. All the refineries have to find out how to get rid of the asphalt, and it is not an easy way to do. And they are very smart. They are throwing that on your driveway, and they're charging you for it, rather than paying you some royalty. They charge you for it. So they're smart. They will find their teeth in order to keep that monopoly out of life. So, for that reason, our success has not been much. What we have had about the success because we are competitors, that's what the Rossi that they would like to have that niche market. Here is an example of a visible picture of an area that includes some grass and some asphalt pavement, and with a thermal infrared image. As you see, the temperature difference is something like at least about 50 degrees Fahrenheit, about 30 degrees Celsius. So when the air brushes on the surface, obviously it's going to get heated and it creates a heat island. So we have been developing some measurement, simplified measurement techniques in order to look at the performance of the asphalt. Obviously, the reflectivity of the asphalt would reduce the temperature of the asphalt under the steady state condition. And principal types of pavements are, this is interesting thing, that you have the word asphalt is used both for concrete and also cement. But when we say asphalt concrete, we are using asphalt. When we say cement concrete, we are using the word concrete. Okay? So the correct way is asphalt concrete versus cement concrete. And the many parts of the world are finding out that it is much cheaper to use concrete, the cement concrete, because its durability and low maintenance for a longer period of time. And for the asphalt, we have never been, or the pavement, we have never been suggesting to change the reflectivity of the pavements from 10% to something like 70%. We say that this is the jump that we can make. This jump is already available in the technologies out there at reasonable cost. Sometimes that reasonable cost is negative cost. There is also another factor that makes this industry very fragmented, very hard to achieve or to make contact with. Asphalt is being applied in many, many different applications, and each of them have a different ownership, different policies are required. Parking lots, alleys, driveways, bridges, plazas, playgrounds, streets, roads and highways, sidewalks, runways. So airports are in charge of the runways. You have to reach different crowds in order to convince them to use reflective material. The streets, roads and highways are being under the control of the city, municipality, and sometimes the state, sometimes the federal government. So with all of that, it is kind of hard to achieve different progresses. But the technologies that we have reviewed, and I'm going to review this thing in detail tomorrow, covers a technology which is called chip seal. Chip seal is rather than mixing the aggregates with asphalt, and then laying them on the ground, we pour the asphalt first, and then put the granules on top of it and roll it in. Therefore, if you have a reflective granule, you can immediately have a reflective surfaces. You can, of course, use light color concrete. You can use coatings. You can use grasscrete. Grasscrete, I saw in several of the driveways in here that the parking lots are made from concrete blocks. These concrete blocks can be support of vegetations to grow out of them, and they make these things pretty cool. And then on top of that, you can use colored material as well as using porous surfaces in order to keep water flooding also under control in this technology. There have been several studies going on, and my colleagues in Japan, like Rossi and Moriyama-san, have been doing some measurements of a sample of different pavement materials and looking at their pictures, infrared at one time during the day, and also looking, following up their temperatures, and therefore identifying which one applies for where and when. One thing very important about the pavement industry is this shown simply in this graph. This graph is test of the pavement performance under the sun. Consider that you have a bus stop that is made from asphalt. This bus stops and picks up passenger and then accelerates go. So every time that it stops, it pushes the asphalt forward. Every time that they try to accelerate, it widens that crack between them. So the depths of these cracks are being known as rotting depths, and they should not be more than 1 centimeter. If it is more than 1 centimeter or 1.5 centimeter, that asphalt is failing. So one of the ways that they design asphalt is that they control this thing under controlled experiments in the lab, that the wheel constantly goes on the surface. And then they count the number of the repetitions. A hot asphalt at 50 degrees Celsius has failed after about 20,000 cycles. A cold asphalt only by about 10 degrees Celsius, which is very much achievable with today's technology, has been going strong after about 180,000 cycles. Asphalts do not fail only because of this factor, but this is one side of it, that if you design a good asphalt, that it only lasts 20% more, longer. In a way, your present value cost would be, or annual present value cost would be 20% less, and assuming that in every country, such as the United States, our annual budget is $150 billion for the asphalt pavement every year. So imagine what a big effect it is having here. If you save 20% of that, $30 million. I think that I can comfortably retire with that money. Most of you probably do. Now, we have also been studying the benefits of vegetation, and I'm only going to show a couple of slides on this one, but that has been, again, a major area of research. We conducted an experiment that we took large trees from 2 identical houses. We brought them on one house, continued monitoring their performance, then we brought the crane, moved them after a month to the next building, continued their performance. So we documented a shading savings of as much as 15 to 20% in cooling energy use. Evaporative cooling, trees, by the process of evapotranspiration and photosynthesis, they convert some of the sensible heat into the latent heat.
that cools the environment a little bit. It actually doesn't cool the environment a little bit. It doesn't allow the environment to get heated as much. Steam, it heats the environment, but comparing to the case that there is no evaporation, it will be heated a lot later. Then trees are being used both in hot and cold climate for wind shielding. In hot climate, to protect the building from the hot wind in a specified direction. In the cold climate, particularly from the northern wind, evergreen winds. So this is another benefit. A smart reduction, trees, not just because of reducing the urban air temperature, they also can, by reducing the urban temperature, reduce the urban smog by about 50%, and the other 50% comes from some good benefits. Trees, leaves are acting as a good filter. The particulates that are harmful to the people, particularly large particulates, these are particulates of 10 micron or larger, they would be deposited on the tree leaf, and tree leaf, because of being slightly moist, they would attract them, and they would not be moved by the wind. When the rain comes, they wash it to the ground where they belong. Dry deposition is also a factor that through the photosynthesis process, trees get some of the ozones converted into the oxygen. And finally, trees, we all know, particularly in this lab, because of the biomass growth, which sequesters some of the CO2 from the atmosphere. Now, the energy savings of trees because of the shading and reducing the CO2 emissions coming in from a biomass that would generate that electricity is 10 times larger than the direct sequestration. So, something to consider. Other measures that we have been constantly working in this integrated research, roof gardens. I am not a big fan of it because of the economy of it, not because of its effectiveness. A roof garden typically is 4 to 5 times more expensive than a typical roof, and you cannot justify that additional cost by the energy savings. Green walls, an old technology that is being used in Europe a lot. Anthropogenic heat reduction, district cooling for cooling urban heat islands, outdoor evaporative cooling. This technology was used in, I think that Olympic 1988, was that in Barcelona? There was one of these years that Olympic was held in Spain. How many of you are fans? You must all be following me. Was it 92? Okay, yes, 92. They use this evaporative cooling. So they have a small mist coming on the pathways, and they created local cooling for the comfort of the people. And of course, energy efficient community design that nowadays becoming more and more the word of the sexy word of the research, zero community designs, net zero design, of how to convert our communities today, which are not very efficient, to energy efficient communities 50 years from now. You cannot demolish all the buildings and build a new facility. You have to do it in a controlled way. So let me talk a little bit about the roof garden. And this is an example of some of the roof gardens that is being applied. This is in Chicago area. This was taken at the time that the roof garden was established. A year after that, it was all dry, not attended. So because of the increment, this costs about $20 a square feet versus a typical roof which costs
$3 a square foot. And this requires an annual maintenance depending on the facility of at least $1 per square foot per year. A typical cooling roof doesn't have that one, and so on and so forth. Now, having said all of that, I spend a lot of money in my own garden in order to enjoy it. But I do not justify it because it is energy efficient. I justify it because that's my style of living. In some places, such as in downtown areas in New York, when the green spaces are not really much, having a roof garden for the people to go and enjoy a comfortable lunch there increases the productivity significantly. So that is the issues to think about it. So may cost significantly more like cool roof, higher maintenance costs, an expensive option in climates that water is scarce. So now, opening another Pandora's door or box, this time looking at the air quality. The air quality of the urban areas and that we are going to discuss, and this is something that I'm proud to say that we are organizing a conference next October in Venice, and about 50% of our papers are focusing on this. If you have a cool surface that would reflect more incoming radiation, keep the surface cooler, air temperature would be cooler, ozone production would be slower, you have less ozone. Now, if you have cooler surfaces that would reduce your energy consumption, that also reduces your emissions, ozone will be lower. At the same time, if you have cool surfaces, the boundary layer thickness during the summer is going to be thinner. If the boundary layer is thinner, the smoke that is being mixed in that thinner boundary layer can have higher concentration. So this is a negative cycle. So one has to really understand all these things. Then, if you have a lot of vegetation, vegetation have emissions that you have to account for it. Dry deposition, vegetation affect the roughness of the surface. With that, they change the velocity field. Velocity field moves the pollutants in a different way if the velocity well changes. They have the evapotranspiration that cools the air, and also their reflectivity may be lower than the asphalt, and they also have lowered the surface temperature. So looking at this whole thing is a big project. So the tools that we have been using and constantly have moved to more stronger tools. We initially started the CSON model, Colorado State Energy Model, then we migrated to MM5. Nowadays, my students are using WRF, world research, weather research forecasting. There are some specialized models, such as San Jose State model that he's the author and a couple of his affiliates using it. ANVIMED does a very thorough energy balance for a neighborhood at the level of canyon, building by building. So it is also being used significantly. For photochemical processes, there are quite a few models that are being used. And the most advanced one at the time was developed by CIT, that is about 15 years ago. But nowadays, WRF have a photochemical component that no longer is needed to do these things separately. You can do it collectively together. Here is an example of some of the research that we did. Here we simulated the entire Los Angeles basin. If I'm not mistaken, this is about 400 by 250 kilometers. The pixel size are about 5 kilometers each. And we planted 3 trees per house, one on the west side of the house, 2 on the southern part of the house, and depending on the density of the houses, so we had different tree plantation, and we came up with a total temperature reduction anywhere going from half a degree Celsius to about 3.5 degrees Celsius. Remember that the areas that has most population of trees have a larger temperature drop. Then we compared the effect of this thing on the air quality, and this is the cooling of the Los Angeles basin, and this is reduction in the smog formation. In some areas, the reduction in smog formation is something like 30 to 40 parts per billion. Some of you may not have an appreciation for this thing. There is an organization in Southern California which is called South Coast Air Quality Management District. And they give their arm and shoulder if they have one single measure that can produce 1 part per billion reduction in the ozone formation. They follow everything. They follow emissions from all the stationary sources. They follow the emission from your gas burner inside your home. They follow the emission from the gas cooktop. They follow the emissions from the dry cleaning that are using a lot of NOxes. So everything that they do, if they are 100% successful, it would be only reducing this thing by 10 parts per billion. Now we have here one single measure that can potentially improve air quality on the average by about 20 parts per billion. So this questions the entire validity of that organization, that everything that is dropped down is peanuts compared to what we can achieve in here. They said, okay, that's good. We would do this thing for everything. So this is a measure that everybody should do. Therefore, they make this thing as their base. So that is our coming in, talking to the leadership of the policymaker and the decision maker to adopt these policies. Because without that, you would not have much of an effect. Today, with my friend, Professor Rossi and Professor Federico, we were talking about how to encourage the politicians and the policymakers in Europe to get more engaged. And I was just telling them of some of this experience. Now, here is the last part of the science and application, is the part that I did not show that in the overall chart. It is the global cooling of it, which I call it geoengineering 101. If you have cool roofs, cool pavements, that would save energy at about $50 billion throughout the world if it is fully implemented per year. Now, if you have cool roofs and cool pavements, that would reflect some of the solar radiation back to the space, and in a way counters the global warming. This is known as radiative forcing, and this particular is known as negative radiative forcing. As you know, by melting of the snow caps on the earth, we are changing the reflectivity of part of the earth from 80% to 5%. And that accelerates the melting down of the snow. And as you know, that Greenland has been reduced, the snow cap on Greenland has been reduced by something like about 30% within the last 20 years. So, what is the typical geoengineering? They're working on 2 basic technologies. One of them they call solar radiation management. The other is greenhouse gas remediation. Solar radiation management includes a lot but the most popular is seeding the atmosphere with sulfate gases, particulates, that would increase the reflectivity of the atmosphere by increasing the clouds a little bit. Such a thing, we may end up on some drastic condition to take these drastic measures. If we really come up to the conclusion that if we don't do things like now, 20 years from now, half of the population of the world cannot live anymore, we may come up to that decision. But this is something that we haven't tried at the larger scale. We do not know any consequence of it. But we have all installed a cool roof for thousands of years in the Mediterranean and Middle East, and we do not know any negative aspects of it, and we continue doing that. So that's the reason we call it the geoengineering 101. There have been also some crazy ideas of bombarding the moon with black paint. So that would make the moon dark, so the reflected radiation from the moon on the Earth is very small. When you do the calculations, you will find that that only affects the net incoming of radiation on the Earth by 0.04 watt, very, very small amount per meter square, which is nothing to the problems that we have. And so I made a joke on BBC that I like every now and then walking under the moonlight with my wife and enjoy that, and I don't want anything to take that away from me. Then the other measures, such as greenhouse gas radiation, is sequestering carbon from the atmosphere by having some biological processes, such as in the shallow part of the world, by upwelling the nutrients from the bottom of the sea to the top layer of the sea. They promote the growth of the algae. Algae would absorb the CO2 directly, and then by dying down, they would take the CO2 in the form of carbon to the bottom. So at all of these things, they have two particular characteristics. None of them are being tested, so you do not know if there is negative effect. And on top of that, we cannot test them because they're so huge a scale that by the time that we know of any negative aspect of it, it may be too late. The other one, they are very, very expensive proposition. So how does this calculation has been done? In Perugia, I am proud to say that independent of our work, Professor Katana and Professor Rossi have been also working on this area and also doing some actual experiment to demonstrate this effect. Here is the way that it simply works. If you take a ton of CO2 from atmosphere, you cool down the atmosphere by a certain degree. That certain degree may be very small, but that's what you do. If you also increase the reflectivity of a surface by a certain amount, you also cool down the temperature of the globe. So at what level this reflectivity is corresponding with the same CO2 emission reduction? That has been the focus of this study. So if you look at the whole balance of the globe, about 340 watt of energy comes in, 75 watt of it is directly reflected by the clouds, then about 67 part of it is absorbed by the cloud, almost 40 to 50%. About 168 watt comes in on the surface and absorbed by the surface. About 30 watt is escaping the earth and reflected. We are suggesting to increase this 30 watt, or at least 30 watt, by a very, very, very small fraction. And I'm going to show what that fraction is. So suppose that we all know that the land is about 29% of the surface of the globe. The cities, depending on how it is being defined, are cover anywhere between 2 to 4% of the dry land. So we are suggesting to increase the albedo of 1% of the cities which are happening between plus or minus 45 degrees latitude by a modest net 10%. And I'm going to say what that is. So we did some simulations, and simulation indeed actually proved that we increase the reflectivity of 0.1%, we get significant amount of the, not 0.1%, 0.1 reflectivity increase, we get significant amount on the temperature. So our analysis was done on long-term performance of the surface, and we did simulation for almost 1,000 years. But in here, we are only summarizing for about 300 years. And we followed several base cases, and then we increased the albedo of the dry land between plus or minus 20 degrees latitude, plus or minus 45 degrees latitude. As you see, if you have higher increase of the land area, the temperature drops, and then it eventually goes back. And this is business as usual growth of the greenhouse gases. Now, if you look at the temperature, you would find out the temperature goes and level out at this level for the base case, and this is for aggressive greenhouse gas reduction, and then the increase of the albedo would significantly lower the temperature. Now, if you look at the temperature difference between the base case and albedo modification, you would find out that about 3 degrees Celsius reduction between 45 and plus or minus latitude, and about 1.5 degree reduction in the Earth's atmosphere, it is happening. And finally, when you make this thing equivalent to CO2 emission, you would find out that increasing the albedo is offsetting about 1 meter square of the land by 0.01 change in the albedo. It's offsetting about 7 kilograms of CO2. So now, suppose that I have a roof. This number now it is in use around the world more and more. So I have a roof that its reflectivity is 20%. I increase it to 60%. So changing the reflectivity is 0.4. I multiply that 0.4 by 7 kilograms. Okay, that's really 40, because for every 0.01 we get 7 kilograms. So you multiply it by the 7 kilograms, you get 280 kilogram offset of CO2 for every meter square of the roof. And if your roof happens to be 100 square meter area, you multiply 100 square meter by 280, you get 28 tons of CO2 reduction in the atmosphere. So we then continue that same analysis, only changing the urban areas, and we came up with this number that if you do this thing only for the urban area, you have a potential to offset approximately 130 gigaton of CO2. Again, that's a large number. You would not be having a feeling for it. Let me put some feeling to it. So this is how we get to that numbers first. For flat roofs, we increase the reflectivity by 0.4. Then for a slope roof, we increase the reflectivity by 0.25. For pavements, you go from the dark color of the dark asphalt to the color of the dark concrete. So put it all together, you would come up with a total reduction of about 120 gigaton of CO2. These estimates that have changed throughout time, initially started with 44 gigaton, now they have gone to about 150 gigaton, is equivalent to 1 to 4 years of the all emissions from all over the world. Now we are starting to talk numbers. If you are thinking about the growth of the emission, if you install your cool roofs and cool pavements, you can basically keep the world stable for the next 11 to 25 years. Guess what? Well, how many years would it take to install cool roofs if you go in the natural cycle of changing the roof every 20 years? If you start program right now, 5% of the roof come to be changed every time on the natural cycle. In about 20 years, you have reached your limit. Another way to look at it, this is equivalent of offsetting of all the cars in the world for the next 20 to 60 years. Money-wise, currently in Europe, each ton of CO2 is traded at $25. So when you put those numbers together, it is equivalent to $1 to $3.5 trillion. The amount of the money that the world will spend in order to get out of the deep recession in the world within the last 5 years has been only $1 trillion. So this is equivalent to 4 of the global recessions. So you can afford it. And on top of that, if you install a cool roof, they keep on reducing your air conditioning bill as far as you're going to keep them cool. This has attracted many attention throughout the world, and we have had stories of this being said on many reports on TV, newspaper. I remember that there were several Italian ones. Do I have an Italian in here? This one? Yeah, correct. Yeah, but because I came more than that. So there were, at one time I counted there was about 1,000 different stories being said. And then we had some leaders who jumped on board with us. This is the mayor, then mayor of Athens, who was the first member to join. Then we had a member of Taiwan who joined us. Then we had Michael Bloomberg, Al Gore, and also Secretary Chu, who was my boss at LBNL. He became Secretary of Energy. He was also our flag keeper for 4 years. So the technology is very basic. It is applicable. And the question is how can we take larger scale implementation? And here has been my plan. We all know that those who of us are interested, that negotiation between the countries, particularly between the developed and developing countries, of how to curb the greenhouse gases has been very difficult, because the developed countries would not like to have the extra burden of carrying out what they have done wrongly for the last 200 years. The developing countries would like to grow fast. They cannot afford the money. And every negotiation, every protocol, and the most recent one, Copenhagen, they failed. So here is one measure that saves us energy, improves our air quality, and cools the globe. It's more attractive to the developing nation than the developed nations because it saves them hard currency in the developing nations. And it saves, and it is good in 3 ways. And let us see whether we can develop some international program that work on this positive aspect, that it is on every country. And if we cannot really put a program together that is helping us all in a positive way, then we are going to have less success when it comes to talking to more serious negotiations. So we better be successful. We cannot afford to miss this opportunity. So I started this campaign for 100 Cool Cities initiatives. Then, as soon as that campaign started, I also started an organization which is called Global Cool Cities Alliance. And me and a few of my colleagues are serving on the board, and I am serving as the vice chair. I do not have the time, unfortunately, to be involved in the day-to-day activity. We have hired a very energetic executive director who is in contact with us and is following our directives. Our mission is to promote cool buildings, cool cities, and cooling the world. It is open to all the cities around the world who would like to join us. So what it would take for the cities to join us, the commitment that they are serious to do something. What we will do is that we will do anything in our power to help them to do it. So at this time, the cities that we have are quite few in here. And I showed this same slide in Modena 2 years ago, and I was hoping that I have a few more Italian photos in here, but it didn't happen. That just says that, you know, I've not been persistent enough. And so all the blame is on me. Now this is actually another interesting thing, that cities are different. In a practice that works in one city may not work in another city. Countries are different. And here are some examples of this thing. You would find out here is New York City. When we talk about city, majority of people would focus around downtown Manhattan area. But look at this huge landscape that it is mostly 2 or 3 story buildings that are dark. So this area, compared to this area, is only about 2%. So you develop some programs over here, which is this one, but you can also focus on a lot of this. This is, by the way, Central Park. This is the Midtown. This is the downtown. This is where the center of the world economic pollution is. Wall Street is right there. This is Perugia. And as you see, I promise you that this area, if you look at it, it is practically 100% roofs and pavements. Obviously, because of the historic region there, we would like to keep these colors of these things out there. There are some products that we have tested in Italy of clay tiles. Then they come in 2 categories. Some of them, red clay tile, 45% reflectivity. Some of them red clay tile, 22% reflectivity. The only difference between them is that the clay is coming from quarries. One of them is rich in iron oxide, the other is low in iron oxide. And that creates all the difference. And they are using it. So this is New York City. If you want to see how it looks downtown when with the white roof, this is when the snow is on the roof. You know, it looks as usual. This is Chicago. Again, the downtown Chicago is in here. This is the majority of the area that we are talking. This is Athens, Greece. Thanks God they do not have a lot of tall buildings, so a good program there can reduce the heat under an easy 3 degrees Celsius. Taipei, Taiwan, same story. Singapore, they do have a good implementation of a variety of technologies that can expand it. Beijing is a disaster. You wouldn't believe this thing, and you are going to see this thing in the next picture of mine. And it is a city that is grown without any plans. Yeah? Capitalism is in wildest form. The central government is socialist, there's no question. But when it comes to the economy, purely capitalism. If you are not in the city and you do not see the people there or the signs on the buildings, you can never understand that you are in a Chinese city. It is, for all practical purposes, it's a Western city. And this is Shanghai, the same area, and again, the problems in here are going to be totally different. This is Mumbai. This area of Mumbai is where the shacks are, and they are all roofs. Yeah, just a lot of these people are living in the poorest condition in the world. Yeah. A United Nations program are giving them a scrap white metal rather than dark metal would reduce the discomfort in their way of life by something at least by 50 to 80%, depending on different studies. So what needs to be done? Every city is unique. One has to develop programs to address energy and air quality issues, to develop databases, to develop, based on these two implementation programs that are different for the roofs, pavement, streets, and now there are different entities who are playing this game. They are city government, they are regional government, there are communities, and there are national governments that they have to be incorporated. Every country, they're going to try things that sometimes are not going to be work. They need a feedback system to make sure that their laws and the land developments that they are using the current information and they are constantly update codes and standards. And on top of that, seeing is believing. And if you put a lot of demonstrations together in quite a few areas, people would believe that even further. The type of measures that you need, if you are talking about tall buildings, roofs, walls, pavements, parks, street visitors, if you are talking about the low rise buildings, you have more or less the same end users but in a different intensities. Changing gear, we have been working very hard to make cool roofs the standard in the United States and around the world. I have been working with Hashem 90.1 and Hashem 2.2, and both of them, one of them developed codes and standards for the commercial, the other for residential buildings. Then the cities and states get this voluntary program and they customize it for their own condition, and they become code and standards, enforceable code and standards. So both of these standards have already included cool roofs. State energy efficiency codes have included, such as California Title 24. International Energy Conservation Code has included. It was very much the case that, again, I'm opening another slide door and letting you have a peek inside, that people would come in and saying that this roof has 120% reflectivity. And for an average person who doesn't understand that the reflectivity can go with 0 to 100%, then it is not understandable. They can easily be deceived. So 20 odd years ago, I started this organization, which is Cool Roof Rating Council, that would measure the reflectivity and emissivity of the materials and label them. So the manufacturer know that from a point of authority, they have all this information. Later on, working with the European colleagues, we started the same thing in Europe. India has also done the same thing. Many other countries, particularly in the Middle East, also are following suit. This is what I was talking about, Beijing. This is a picture of the Beijing in 2 days. of the same area. And in December, I was in Beijing, it was like this. And they had to close all the freeways because one could not see 15-meter ahead. And practically all of these things are because of the pollutant matters. They are not even smart. They are particulate matters that are in the atmosphere. With a little bit of control of the refineries and the control of the cars, they can overcome close to 90% of this thing in a period of 2 weeks. And guess what? These are the citizens that are having all black lung. And eventually, the society will pay for this. This is a man-made, and man is paying the consequence. Man cannot do it, man cannot benefit from that undo. So, everything that I have said in here, if you want to forget everything, you are not allowed to forget this one. If you change your roof to that of a dark roof to that of a white roof, you offset 10 to 20 tons of CO2 emissions. These are some references for you to remember. My colleague here in Italy, we are putting together a conference in Venice, October 13 through 15. Yeah, we were initially thinking about having 50 abstracts, and as of the last count of today, we have over 200 abstracts, and we are estimating about 150 people participate. Now we are thinking about 300 to 500 participants, and I'm quite sure that we will be seeing quite new faces out there, at least in the form of volunteers to help us with the organization of the workshop or the conference. And believe it or not, everything that I do in my life is hobby. And this is another hobby that I have. And I try to attend them all. So I am a lover of music, and my appreciation of music has increased tenfold when I started to practice music myself. I've never claimed that I am a professional, far away from it. I'm always a beginner in everything that I do in the world. Here is my coordinates, please. I will be more than happy to answer any question if you have at this time. And of course, any email from friends is being answered if I am available within less than 24 hours. I have been the sole speaker. Nobody asked any question.
Ragazzi, fate qualche domanda.
Can I start with a question?
Why not?
So, we talked about the secondary benefits of higher degrees of phases, like we talked about rules and prepayments, and I'm actually referring to the benefit to the atmosphere, to the offsetting towards the reduction of the CO2. So we also gave a quantification of the economical benefits one could gain in terms of CO2 credits. I'm asking, what happens when those surfaces will be dismantled? I mean, it's like you are making a temporary benefit to the environment, right? So is there a plan, or is there a perspective for what happens after?
Yeah, the idea that since I'm trying to reduce my presentation time, the idea that you have mentioned is There we go. It comes into some basic ideas. First of all, you have to enforce this thing throughout time. If you are talking about energy savings, if you have a cool roof, next day you start putting a dark roof, your energy bill goes up. We are relying on the brain of the consumers that if we tell the consumer and the society that the annual cost savings is in the order of $0.50 to $1 per meter square, and the annual CO2 savings is certain amount, and net present savings throughout 20 years of your roof is 7.5 to 15 years, and the maximum incremental cost that you pay for a cool roof, the maximum. In most cases, it doesn't cost you any more. In some cases, it may cost you less. Then, eventually, we have given enough ammunition to a conscientious customer to make the decision. Okay? Therefore, this is a no-brainer. But like any other thing, we all know that some cars run on 5 liters for every 100 kilometers, and some cars run on 5 liters every 5 kilometers, the large cars. So there are society, when we are living in the society, we are living by the rules. We are no longer accepting individuality as the only factor. So your freedom to move your arm stops when my nose starts. Your freedom to pollute starts when my health is an issue. And we control those things to the societal level. So we are assuming that this is something that we can develop programs on. No brainer. And the next thing is that, how about the cool roof on a slope building? We say that the same economy savings are half, but still a lot more attractive than potential costs. It is something good to go for it. Then it comes to buildings that are not air conditioned. Okay? How are we going to make sure that they are kept white forever? Now, the economy at this time says that if you install a cool roof, a white roof, you offset CO2 by a certain amount. And that certain amount is $2.50 per meter square. So suppose that I get that $2.50 and I sell it in the international credit. And that also requires policy development. Now, I have that $2.50. I come and tell you that if you install this white roof on your building, I give you $1 just to put it in your pocket. You would do that because the incremental cost is zero. Now, the other $1.50, I'm smart. I keep it in a bank and see it grow to $2.50 in 20 years. When the guy comes in to change his roof, I am offering another $1, and I can keep this thing going on. That theory is easy for mathematicians, for physicists, but doesn't really work. How can we work it out? Okay? Or can we basically, in some societies, say that no white, no cool roof is going to be produced? Remember that the market changes. In my lifetime, when I was very interested in photography in my early ages, I could not afford a color film because it was 4 times more expensive than black and white. 15 years ago, I was trying to be artistic, take some black and white pictures. Guess what? Black and white was 4 times expensive than the colors. Nowadays, you cannot find either of those things because the technology has changed. So that also plays a role in here. And then finally, it comes to the pavement. Pavement is savings that you get is something like $1 per meter square of global cooling effect. Now, if the pavement costs you 0 incremental cost, you can do it. But if it is going to cost you $2 per meter square to make it light color, you have to come up with some solutions. How to make it work. And one of the ways that, for instance, you can make it work, if you are finding out that the cool pavement is lasting 20 times longer than a standard pavement. By the way, pavement is typically being resurfaced every 7 to 10 years, asphalt pavement. Now, if you make it every 12 years, the cost of that would be substantially lower by about 20%. That 20% is far more than this $2 per meter square. It's in the order of $5 per meter square. So if again, people will see that it works. So the bottom line in here is that you have to not only look at the science part of it, the economy part of it, but we also live in a society that we can collectively decide in our society of how to implement measures that are good for everybody. Still in a free, individualistic society, but the issues that affect all of us, we would control. My pleasure. So,
Hashem, we have been talking about numbers,
yes,
which compares the effect to the economical value.
yes.
But my question and my suggestion is who controls that number? Is there an agency? Is there a proposal for an agency to control, to check this number? Who controls the efficiency of cooler roofs? We have to think to something like an agency to do this work. I think that
You're absolutely correct. Let me tell you about California. In California, they develop codes and standards for buildings. So the California codes and standards have evolved from year 2000, then they have the cycle of 2004 standard, then they have the cycle of 2008 standard, and each level, the standard became more and more progressive. So in 2000, the standard said that if you install a cool roof, we will allow you to install lower insulation on your buildings. So that would save the building owner or constructor something. Then, second part is that if you are installing a white roof, if you are installing a roof that's 2004, it is societally more beneficial for the whole society to do it. Now it became law of the land. Every single construction that goes in California, they need to have a permit. So if you are going to install a roof, you need to have a permit. And that permit has to be done by a professional engineer. So you cannot go and install a black roof today. Whether that applies to the condition of Italy, the answer is most probably no. You have to find out how it works in here and make it happen.
But the sense of my question is a little bit different.
Yes.
You are talking about the rules, about the laws. I mean, which is the authority which controls the aging and the performances of the materials of installation? Since we respond to the law, since we respond to the regulations, after 20 years, after 15 years, probably the materials, the surfaces will lose their performances because of aging, because of many other causes. I suppose that an authority is required to check and to control such kind of, and it is a proposal too, it is not just a question.
No, you're absolutely correct. That is the function of Cool Roof Rating Council. Cool Roof Rating Council, that's the reason that we established that one in the United States. Cool Roof Rating Council monitors and labels the solar reflectance and thermal emittance of the building, of the roofs at their initial values and 3 years age. And the reason that 3 years age was selected was that for majority of data that we have, we find out that the roof solar reflectance depreciate typically on the first year by 80% of the total depreciation ever. Then after that, for the next couple of years, it only depreciates at a slower range. So now if sometimes in the future we came out and finding out that the database has expanded, rather than having 3-year label, we need to have a 5-year label, we would do it that way. That's the reason we say that we have to be independent, we have to have measurable numbers in order to make the best of the society in mind, and also to have a defendable numbers and results. And on top of that, you are always going to be finding some samples that the roof reflectance after 3 years has improved by a certain amount, for whatever reason. Or you are going to find out some samples because it is being buried under half a centimeter of dust is no longer white. But whether these are the majority of the surface areas, that is probably not the case. So the example of the Cool Roof Rating Council and National Frustration Council in the United States is exactly that. It is self-policing of the Manufacturers Association, that it is also controlled by the watchdogs, which are environmentalists.
One question, another question.
Yes, sir.
Which are the, first let me introduce you, Professor.
Yes,
Rossi.
I was introduced.
Yes. Which are the steps for a city, for a municipality to become member of the Cool Roofs Alliance? And
Yeah.
which are the formal steps, and after that, which are the implications and the duties?
The first and foremost, in my humble view, is that I know that I have a partner there that is serious to do that. So if that's the reason that throughout the world I have been working with the mayors of the cities, knowing that they have the responsibility for the cities on the final count, rather than working with the ministers of the countries. So if a country, a city is deciding to do that, they develop a plan. They say that we are interested, we need that. Then we will say, immediately we are all there, let us make this thing formal. You will tell us, write in a plan that you are interested in doing that, you need the help, and you are welcome to our community. And the conditions that I have put forward for this thing is that, number one, you have to be very serious to do that. If you are just there for not doing that, you are sort of basically you are not taking advantage of GCCA. Number two, you should be able to help the others along your way, sharing your experience. Yeah, in most cases people are very interested. Then the rest of it is that up to local intellectuals to help you to develop your specialized plan. And then in cases that your problems, some of the problems are the same with the other problems of other cities, you would come together as a city, find out some integrated implementation plans that you need to develop further, and then we will help you. That's basically been my life in the last 30 years.
Thank you.
Yes. So we find out, if we can get Perugia interested in that, and then you would find out how many times per week, per month, per year you would see me here.
I think that I don't know, Perugia maybe some difficulties about historical heritage, but tell me, I think it may be a suitable city to take part of the initiative, because it is an industrial city, and I think that there are many places in which cool roofing may be easily permitted.
Sure, absolutely. Again, when we look at the new development area, there are the population of most part of the world has increased from 500 million 100 years ago to 7 billion now. Now, these are not people who are living in the interior part of Roma or interior part of Perugia or Bologna. They are all living in the outskirts, and they are all following the same practices that are being followed in new development. So easily all of these things can be members. And we can exclude for the time being all those historical regions because they are going to be very smaller part of the whole city to begin with. The same way that we did it for New York, saying that downtown Manhattan, we are not going to be focusing once. That's the same thing that we would do for the other regions.
If you have no other question,
How many of you are graduate students here?
quanti sono laureati?
Did you know that there's going to be a quiz on this thing on tomorrow afternoon? I hope that you are well prepared for that. I will give you a quiz. I'm actually, I do not know why you are not asking any question. I am hoping that I have been talking slow enough for you to absorb the details of it. And I have not lost you in between.
I think that's all.
Okay then, perfect. Thank you. Thank you very much.